My name is David Carlisle.
For my E511 project, I put together a buck power converter, DC to DC converter.
Starting with a 9-volt battery as my supply, I'm going to create a circuit that produces approximately 3 volts and provides feedback to maintain approximately 3 volts. First of all, I'm starting with a step signal using a timer chip. This timer chip is creating a step input signal to my switch. For my switch, I'm using a NPN transistor. I attempted to use a MOSFET, but I was not having a lot of luck with that, so I went to the transistor. I also have a relatively large diode and a relatively large inductor. This is a 500 microhenry inductor. And through the buck circuit, I also have a 470 microfarad capacitor. Running at about 7.5 kilohertz. If I was just to use the timer circuit itself as my my signal, my off and on signal, I would wind up with about 6 volts, but I'm going to target 3 volts. So what I have is I additionally put in a operational amplifier using the op amp as a comparator circuit, and having a set point adjust at approximately 3 volts. Then I'm going to take my comparator circuit output to an AND gate, and when both the op amp is true and the timer is true, it will give a signal to turn on the transistor. The transistor turned on, of course, will charge the inductor and turn off the inductor at the proper time. So right now I'm going to show just a quick look of the signals. What you have here is at a very low load. We have the primary timer circuit signal, and then this is this signal outside of the AND gate for the transistor signal. Ultimately, this is the duty cycle to the transistor from approximately this zone with a see, you got 130 millisecond on the bottom and about 20, so I don't know, a little better than a 10% duty cycle. And with that, I get an output. I'll put my output on here. Oh, first I'll show something. Running this, you can see I'm going to change my load, and you watch the blue line stretch out a little bit to increase my duty cycle. It's a change in load. The original load's pretty low. I have 470 ohms across a diode. And the other load is I have a 47 ohms, so basically 5 times the load. Well, 10 times the load when I touch my switch here. Touching the switch, notice a little distortion on the timer circuit, and that the output from the AND gate is almost as long as the output from the timer itself. One second, I'm going to freeze this here. So now I've gone from a duty cycle of about 20 milliseconds to a duty cycle of, let me this to move. "75 milliseconds over 130, almost 50% on my duty cycle, from 20% to 50%. And that's how my voltage is maintained for this project. All right, let's get some voltage indications here. I'll have duty cycle and voltage now. Voltage is a nice 3.068. This is adjustable through the comparator circuit. Dial it up to 3 point. All right, a little more. I want above 3. We'll say 3.2. And when I increase the load, you'll see the duty cycle, the blue line expand, of course. The voltage will drop a little bit, but the behavior is pretty good, actually. So I'm going from 3.2 to 3.1 almost. And it's maintaining that voltage as the best it can with changing the duty cycle. So again, I'm basically just using a op-amp comparator circuit for my feedback and combining that with the AND gate back to the transistor from a switch, turning the switch off and on. I'm continuing to use the timer circuit to make sure I have a real on and off time, and I'm not just sitting on an op-amp making a lot of noise. This kind of, the timer circuit forces a sufficient delay, or that, especially with loads, that the op-amp isn't just sitting right on the set point back and forth. So I think the project worked pretty good. It was a lot of fun, and it was a good class. Thank you very much.